All right, if you're in finance or economics, listen up. Today, we're going to crack open one of the most powerful and frankly coolest tools in your entire statistical toolkit, the moment generating function, or MGF. This is your secret weapon for looking past simple averages to see what risk really looks like. Let's jump in. We spend so much time calculating things like average returns and volatility. But what about the really big, scary questions? How do you actually put a number on the risk of a sudden, catastrophic market crash? Turns out your standard mean and variance just don't cut it. They don't give you the whole picture.
And that right there is the core of the problem. Your standard metrics, they can be seriously misleading because they don't capture the full story of risk. To see the hidden dangers, we're talking about the potential for extreme portfolio-killing losses, we have to look beyond the basics. We need to get into something called higher-order moment.
So, what on earth are these moments? Well, think of central moments as a team of statistical detectives. They're here to tell you everything about the precise shape of a probability distribution. You know, how symmetric it is, how peaked it is, and, most important for us, how fat its tails are. Understanding these is absolutely crucial for getting a real handle on financial risk.
Okay, now this is where it gets really interesting. Look how these moments translate directly into finance concepts we care about. The second moment, variance, that's just our old friend volatility, or standard risk. But the third one, skewness, tells us if our returns are lopsided. Is there a bigger chance of a huge loss than a huge gain? And then there's the fourth moment, kurtosis. Now that's the big one. This measures tail risk, the real probability of those rare, extreme, black swan market crashes.
So, what's the catch? Well, if you try to calculate something like skewness or kurtosis using their textbook formulas, especially for more complex distributions, it's a total nightmare. Just a messy, tedious grind of integration or summation. But luckily for us, there's a much more elegant way to do it.
And that elegant solution is the moment generating function. Seriously, I want you to think of it like this amazing mathematical machine. You feed a probability distribution into it, and you can get any moment you could ever want out of it. And you get it cleanly and super efficiently.
So, what does this machine look like under the hood? It's defined as the expected value of e to the power of ty. Yeah, I know, the formula itself looks a little abstract, but trust me, the name tells you everything you need to know. Its entire purpose, its reason for being, is to be a factory that generates all the moments of a distribution, on demand. So how in the world does one function hold all of that information? Well, the secret sauce here. It isn't really magic, it's pure math. It all comes from one of the most powerful ideas in calculus, the Taylor series expansion. Let's break down how this actually works. Here's the core insight, the whole game, right here. When you expand the MGF into its Taylor series, the moments are just sitting there, plain as day, as the coefficients of the series. I love this analogy. The MGF is like the distribution's DNA, and the moments, they're the specific genes encoded right inside it. All the information about its shape is baked in from the start. Okay, so obviously we're not going to sit here and try to read coefficients from some endless series. That's just not practical. But that underlying DNA structure gives us an incredibly simple and powerful shortcut for pulling out those moments. We're going to call it the derivative trick. And honestly, the recipe is as easy as 1, 2, 3. Step 1, find the MGF for whatever distribution you're looking at. Step 2, take the derivative. How many times? As many times as the moment you want. Want the fourth moment? Differentiate 4 times. And step 3, just plug in t equals 0. Boom, that's it. The number that pops out is your moment. Okay, the theory is great and all, but let's actually put this tool to work. We're going to start with the Poisson distribution. And this is a super common one in finance for modeling the number of times an event happens, like say the number of trades per minute, or the number of insurance claims per day. So for a Poisson distribution, the MGF has this really clean and elegant form, where that little lambda symbol just represents the average rate of events. Now that we have our function, our machine, we can just apply that derivative trick we just learned. Watch how easy this is. We take the first derivative, plug in 0, and we get lambda. That's our mean. We take the second derivative, plug in 0, and we get lambda squared plus lambda. Now to get the variance, we just take that result and subtract the mean squared, and we're left with just lambda. How cool is that? We just effortlessly confirmed a famous property of the Poisson. Its mean and its variance are exactly the same.
All right, that was the warm-up. Now for the main event. Let's see what happens when we unleash this powerful theory on real, messy market data and see what hidden risks we can find lurking in the S&P 500.
This gets us to a huge, foundational question in finance, one that a lot of classic models just kind of gloss over. They're often built on this core assumption that asset returns follow a perfect bell curve, a normal distribution. But is that really true? Let's put it to the test. So, we crunched the numbers on the daily returns of an S&P 500 ETF. First, the skewness is negative. That suggests big down days are a bit more common than big up days. But look at that kurtosis. 16.1. Let me say that again. 16. For a perfect textbook normal distribution, this number should be 3. This isn't just a red flag. This is a giant blaring siren telling us we have fat tails. So that huge kurtosis number is our first major clue. But this is where the MGF really shines. Instead of just comparing one number, we can compare the entire story of the distribution. We can take the generating function from our real data and put it head-to-head against the MGF of a perfect theoretical normal distribution. This gives us a much, much more complete picture. Okay, look at the numbers here. The empirical MGF, that's the real world calculated straight from the S&P 500 data. The normal MGF, that's the textbook fantasy world, what it should be. Now look at that difference column. See how as we move away from the center, that gap between reality and the model doesn't just grow, it grows exponentially. That growing gap, that is the mathematical signature of fat tails. You don't even need to be a math whiz to picture what's happening. If you plotted these two functions on a graph, you'd see them start off close together near the middle, and then, whoosh, they would fly apart from each other out in the tails. This is the smoking gun. It is the undeniable visual proof that S&P 500 returns are fundamentally not normal. Period. Okay, so what's the bottom line here? If you're a risk manager, or you want to be one, what do you do with this? Well, first, that negative skewness means you have to plan for asymmetric downside risk. Second, that massive kurtosis means those extreme crash-like events are way more likely than your standard models are telling you. The MGF divergence proves it. The biggest takeaway? Assuming returns are normal is dangerous. It means you are systematically underestimating the real risk of a market crash. All right, let's wrap this up. What are your big MGF takeaways? Number 1, MGFs are like a fingerprint. They uniquely define a distribution. Number 2, they give us that awesome derivative trick to make calculating moments a breeze. 3, they are absolutely essential for doing risk modeling right. And 4, they are the ultimate proof that just assuming market returns are normal isn't just lazy, it's dangerous. Ultimately, I think this sums it up perfectly. The MGF doesn't just give you a few numbers. It gives you the entire story of risk, all packed into one elegant function. And that's what I want to leave you with. Now that you can see these hidden risks, the fat tails, the asymmetry that standard models completely miss, how does that change the way you would think about building and protecting a portfolio? That's a question every single one of us in this field needs to be thinking about.